Hello everyone. I am Akshay Kumar De, Assistant Professor from the Department of Chemistry of Bremen University. Today, I will discuss an important topic which is very relevant in the first semester curriculum of BTech students, that is water chemistry. So, as future engineers, whether you are working in software, infrastructure, or electronics, you may wonder why study water chemistry in a BTech course. The answer is simple. Water is essential not just for life, but also for nearly all types of industrial and technological processes. From cooling systems in data centers to semiconductor manufacturing, water quality and treatment play a crucial role. So let me introduce about the topic water chemistry. So water chemistry is the branch of chemistry that deals with the study of the composition, structure, physical and chemical properties of water, the behavior and interaction of water molecules with other substances, and how the composition, quality, and treatment of water in various contexts like industry, environment, and biological systems. So, in simple terms, water chemistry helps us understand what is in water, how it behaves, and how to treat or purify it for safe use in homes, industries, and nature. For example, in your daily life, you must have seen or noticed various phenomena regarding the water. Firstly, how is drinking water treated to make it safe? Then, secondly, why does soap not lather well in some kind of water? And thirdly, why do scales form in industrial boilers? All these questions can be answered through water chemistry. So, in this discussion, we'll be basically explore topics like the structure and properties of water molecule and hardness of water, its types, causes, and the treatment methods. So, let's begin exploring this essential topic. So, first, we should discuss the structure of the water molecule. So water actually comes with the formula of H2O. So you can see one oxygen molecule with 6 valence electrons and two hydrogen molecules with one valence electron each. They will combine to give the water molecule which actually gets a bent shape. And from the hybridization theory or the BBT, we get the geometry of water as distorted tetrahedra. The bond angle between hydrogen and oxygen becomes almost 104.5 degree and the oxygen hydrogen bond length is 95.84 degree, and due to the presence of these two lone pair of electrons on oxygen, water becomes a highly polar molecule. And here you can see the another models, that is the ball and stick model of water and the space filling model. So let's discuss some basic properties of water. So freezing and boiling point of water we all know as 0 degree Celsius and 100 degree Celsius respectively. So these two temperatures are taken as a reference in the temperature measurement. Specific heat of water is 1 calorie per gram. That means 4.18 joule per gram. So due to such a higher specific heat, water is used as boiler industries and as coolants in different vehicles. Water also have a very high surface tension, that is almost 72.8 kilonewton per meter at 20 degrees Celsius, and the viscosity of water is 10.02 millipoise at 20 degrees Celsius. So as the temperature increases, that means at 30 degrees Celsius, the viscosity of water is almost 8.0 millipoise. That means viscosity decreases as temperature. And as I have just said in the earlier slide, that due to the presence of two lone pairs of electrons in water, it is highly polar in nature, and due to this polar characteristic, ionic compounds such as different salts, alcohols, and acids, etc., they easily dissolve in water and make water as a versatile solvent. Water is also amphoteric in nature. That means it can act both as acid and base, as it can produce both the H plus ion and H minus ion. But we must remember that At constant temperature, the number of hydrogen ion produced by water is equal to the hydroxide ion produced, and their product is always a constant. The product is always constant. The pH of pure water is taken as 7. That is also a reference in the pH measurement. Now in this slide, we will see the sources of water. So water exists on our planet as hydrosphere, and this hydrosphere is distributed throughout this planet in different sources. That is the surface water. It includes the running water from streams and rivers, and stagnant waters, that is from lakes, ponds and reservoirs, etc. Underground water is a major source of water, that it includes water from water table itself, in wells and springs. Some other water remains in the atmosphere as moisture, okay? And this moisture is further converted into rainwater, and it will come down to earth's surface as rainwater. And obviously a very large amount of water is present in sea and ocean as saline water. Now, as our main focus of discussion is the hardness of water, it's actually regarded as one impurity of water. So in this slide, we will discuss about some specific impurities of water. As we have discussed earlier, water as a resource is very much vital in our life, especially for drinking purpose, that is the potable water. So the water must be freed from any type of impurities. So the impurities of water can be broadly classified in the following categories. First is the dissolved impurities. These include the dissolved salts of carbonates, bicarbonates, chlorides and sulfates of calcium, sodium, magnesium and iron, and many other metals. It also contains some dissolved gases like O2 or CO2. And you can see these types of impurities, these type of salts, they are fully soluble in water, making the water transparent, as you can see in this figure. Okay, so it is transparent and water can clearly pass through it. Then the other type of impurities are suspended and the colloidal impurities. So this is the colloidal impurities and this is the suspended impurities. So they look very similar, but just the difference between them is in the particle size. So the colloidal particles are smaller than the suspended particles. Here the particle size range between almost 1 to 100 nanometer, and here the size is greater than 100 nanometer. Okay, in both cases the water becomes hazy, that is translucent. Okay, but these particles, they cannot be seen through naked eye, whereas the suspended particles, they can be seen through naked eye, and they basically after some time precipitates down at the bottom of the container. So the suspended impurities are the inorganic impurities such as clay, sand, and organic impurities such as oil globules, animal and plant matters, and the colloidal impurities are very finely divided organic matter, silica, clay, then the dead body matters, etc. So in this slide, our major focus is to discuss about the hardness of water. So hardness is the property of water by virtue of which, that means due to which, it fails to form lather, that means foam, when soap is added to it. So this is due to the presence of certain types of dissolved salts of calcium and magnesium and other heavy metals such as iron, aluminium and manganese. So more prominent is the calcium 2 plus and magnesium 2 plus salts. So these are the cations, and anions are basically the bicarbonates, that is HCO3 minus, then the carbonate, that is CO3 2 minus, then the chlorides, that is Cl minus, and sulfate, sulfur 2 minus. So the presence of these type of cations and anions gives rise to different types of salts, and when these salts are present in water in higher amount, they make the water hard. So hardness is of two types, that is temporary hardness and permanent hardness. Temporary hardness is attributed to the presence of dissolved mainly bicarbonate salts of calcium, magnesium, and other heavy metals. That means mainly it is the calcium bicarbonate, CaHCO3 whole 2, and magnesium bicarbonate, that is simply MgHCO3 whole 2. So this, why this is temporary hardness? Because this type of hardness can be removed easily by boiling the water. So in this process, these bicarbonate salts, when they are heated, that means when heat is given, they can be decomposed easily in insoluble carbonates or hydroxide, which finally settles down as precipitate at the bottom of the vessel. So this hardness is also known as the carbonate hardness. So you can see calcium bicarbonate can be precipitated as both calcium carbonate as well as calcium hydroxide along with the evolution of some carbon dioxide and water. Another type of hardness is permanent hardness. As the name says, this hardness is permanent because it cannot be removed merely by boiling the water. Just if we boil the water, if we just heat the water, the hardness cannot be removed. And this hardness, permanent hardness, comes into water due to the presence of chlorides and sulfates of calcium, magnesium, and some other heavy metals. So basically, it is calcium chloride. The possible salts are calcium chloride, then calcium sulfate, and magnesium sulfate. Okay, so they cannot be removed by just boiling the water. So here, for the removal of permanent hardness, we actually have to adapt some chemical treatment. So that's why these hardness is also known as non-carbonate hardness. So in the adjacent figure, you can see this hard water contains calcium 2 plus and magnesium 2 plus. So as the concentration increases, the water becomes soft to hard. So we will be discussing the unit in the next slide. But here it is ppm, that means parts per million, and GPG, that is gram per gallon. So whatever the unit is, you can see here as the concentration of these ions are increasing in water, that means the water is becoming from softer to hard. Now, the most common technique to determine the hardness of water is the soap test. That means just by looking at the foam formation with soap. So soap are basically the sodium or potassium salt of higher fatty acids like palmitic acid, stearic acid, and oleic acid. And this can be done by filling a bottle up to 1/3 with water. So these both bottles are filled 1/3 with water. In first case, it is soft water. In second case, it is filled with hard water. And now some soap has been added to it. So in case of the soft water, you can see this bottle, the upper part becomes full of the bubbles and the lower water remains almost clean. But when the hard water is used, a less lather formation happens compared to the soft water. You can see less lather formation happens. So when the water is harder, also a white precipitate is settled down at the bottom, that is known as the soap scum is produced. And there is a distinct lack of fluffy bubbles and the waters also becomes cloudy or milky. Okay, so hard water. So this is a preliminary test for distinguishing between a soft water and hard. Now, how to calculate the hardness of water? So, hardness of water is usually calculated in terms of calcium carbonate, is CaCO3. So, now the questions arises: why the choice of calcium carbonate is taken? Why calcium carbonate is taken as a reference? So, here the most important reason is calcium carbonate acts as the most insoluble salt that can be precipitated in water. That means whatever the salts presents in water, okay, through heating or through chemical treatment, okay, our main focus is to precipitate them as calcium carbonate because it is the most insoluble salt in water. That's why calcium carbonate is taken as a reference in the calculation of hardness. And next is the molecular mass of calcium carbonate is 100, calcium 40, argon is 12, and 3 oxygens are 48. So 60 plus 40 it gives 100. That means the calcium becomes easier. So the equation becomes hardness in calcium carbonate equivalent, that is we can write H is equal to mass of the hardness imparting substance. That means the hardness causing salt present in water. How much milligram per liter of hard water? So this will be in milligram per liter. That will be multiplied by this conversion factor. So this conversion factor, the upper part is equivalent mass of calcium carbonate. Now we know that calcium carbonate obviously gives a calcium 2 plus cation. Okay, so here the equivalent mass becomes 100 by 2. That means equal to 50. So this numerator part is always 50 in the calculation, and the denominator part is the equivalent mass of the hardness imparting substance. That means uh, the salt we have considered here, we have to calculate the equivalent mass of that salt and put it in the numerator of the equation. So it becomes 50 by equivalent mass Z of the hardness causing salt. Okay. So after calculation, the hardness is expressed in milligram per liter, that is 1 milligram per 1000 ml, so 1 liter of hard water. Okay, so if 1 milligram of calcium carbonate and hardness causing salt is present per liter of water, then it will also equal to parts per million, that is ppm. Okay, so we can say milligram per liter equal to ppm. It is also expressed in such units such as degree French or degree Clark. Okay, so for such units we will use the conversion formula. So degree French is almost degree French is 10 times greater than ppm. So 1 degree French is equal to 10 ppm and 1 degree Clark is equal to 14.9 ppm. So both both units are higher than ppm. Now let's understand the previous formula with this numerical problem. How many milligrams of MgCl2 dissolved per liter to give 60 ppm of hardness? So this hardness is obviously in calcium carbonate equivalent. So hardness is given as 60. So here we have to calculate the mass of MgCl2 in milligram per liter, and the from the previous equation we got the equivalent mass of calcium carbonate is 50, and for magnesium chloride the equivalent mass is magnesium 24 and 2 into 5 is 71, that is 2 into 35.5. So total we get 95, and magnesium gives magnesium 2 plus cation. So the equivalent mass becomes 47.5. Okay, so MgCl2 is equal to hardness in equivalence mass of MgCl2 by equivalent mass of calcium carbonate. So finally we will calculate the mass of MgCl2 per liter 60 into 47.5 by 50. That is 57 milligram per liter. So one thing you must notice here, the calcium carbonate equivalent hardness is 60 ppm. That is with respect to calcium carbonate. So to get 60 ppm of calcium carbonate equivalent hardness in water, we need only 57 milligram per liter of MgCl2. So every salt, every hardness causing salt present in water, it does not give the same amount of ppm. So 57 milligram per liter of MgCl2 in water, that means it is not 57 ppm of hardness, it is 60 ppm of hardness with respect to calcium carbonate equivalent. Now, the here in this slide we will discuss about the measurement of hardness of water by complexometric method. So complexometric titration is a precise analytical method used to determine the hardness of water, primarily caused by calcium or magnesium ions. So hardness of water sample is the parts by weight of hardness causing ions, that means calcium and magnesium both, expressed in terms of equivalent amount of calcium carbonate per million parts of water. So obviously as the unit says, it is ppm. So the total amount of calcium and magnesium ions in water sample is determined by titrating it against a standard PDTA solution, that is ethylene diamine tetraacetic acid, using the EBT, that is iriochrome black tea indicator, in a medium of a buffer of stain. That buffer is prepared by 1:1 ratio mixture of ammonium chloride and ammonium hydroxide. So this process involves a complexing agent, that is EDTA. We all know that EDTA is a hexadentate ligand. That means it has total 6 donating sites. So it is 1, 2 nitrogen and 4 hydroxyl oxygens, total 6. And when this is added with the metal ions, it will form a stable colorless complex of calcium EDTA or magnesium EDTA. But in the titration process, first we have to add the indicator in water sample. Okay, so let's go to the next slide. Here you can see first in the water sample that contains calcium and magnesium, first we have to add the indicator under pH 10, that is maintained by the buffer. So first calcium EBT and magnesium EBT, that is a metal ion indicator complex. It is a less stable complex formed with a red wine color. Now in this complex, when from burette EDTA is released, EDTA is added, then EDTA actually replaces the EBT and from the metal EDTA, that is calcium EDTA and magnesium EDTA, more stable complex, that is colorless. So the EBTs will be freed, okay, and we can see the steel blue color of the free indicator complex. So at the end point, that means when all the hardness ion have complex with EDTA, the end point is indicated by the appearance of this steel blue color. Okay, so here you can see this is the EDTA complex. So through these 6 donating sites, it will form a complex with calcium and similarly with magnesium, and that looks like this type. So this method is widely used due to its accuracy, speed, and simplicity in assessing water quality as well as guiding the further softening treatments. So now we will discuss the hardness softening methods. That means obviously water may have some hardness, but before using it for various purposes like whether it is drinking or industrial or agriculture, we have to put the hardness using different types of chemical treatment. So first process of hardness softening methods is the lime soda process. In the lime soda process, the dissolved hardness causing salts are converted into soluble carbonates or hydroxides by adding a calculated amount of lime, that is calcium hydroxide, and soda, that is sodium carbonate. The insoluble compounds which are further precipitated, they are filtered off. So in the adjacent picture you can see here it is the hardness containing water is inserted, and here the chemicals like lime soda are inserted, and in this portion through using a pedal stirrer it is mixed, stirred. Okay, in the middle, outer part, in the middle we have a fiber filter. So the soft water being lighter, it goes up through the filter and that is collected for further use, and the insoluble compounds which are precipitated from the sludge here, and through this outlet the sludge is actually excreted outside. So reactions involved in lime soda process are here you can see it can remove type of temporary hardness as well as permanent hardness. Okay, so calcium bicarbonate reacts with calcium hydroxide, give calcium carbonate and water. Probably magnesium bicarbonate reacts with calcium hydroxide to give MgOH whole 2 plus calcium carbonate plus water plus CO2. So they does not they do not cause any problem, but magnesium hydroxide formation may further is a problem that I will discuss in the last slide. So now calcium chloride plus sodium carbonate gives calcium carbonate to initial problem, and magnesium sulfate plus NaCl3 gives magnesium carbonate plus sodium sulfate. This it also causes no problem, but magnesium chloride a little less soluble than calcium carbonate. In this slide, we will discuss the advantages and disadvantages of the lime soda process. So advantages are lime soda process is cost effective for large scale operation, it reduces both temporary and permanent hardness. It also can reduce the iron or manganese ion. It decreases the water corrosiveness. It increases alkalinity and stabilizes the water pH against the acidic water. And lime soda process also puts some aids in coagulation and sedimentation process. But the disadvantages are it generates a large volume of sludge, that is the precipitate, which is required to be disposed further. It cannot remove all hardness. That means a large amount of residual hardness remains. It is a major disadvantage of this process. Requires a careful chemical dosing and skilled operation. The process is also very slow, that requires very long settling time. High maintenance due to equipment scaling and sludge is required, and may cause excessive alkalinity. That I just have talked in the earlier slide. The formation of some hydroxide salts, okay, MgOH, the pH increases. That means the pH correction. But next process is the zeolite. So zeolite is a hydrated sodium aluminosilicate, okay, that comes with this formula. So this total part we can abbreviate as Z. So the industrially available zeolite becomes Na2Z. So the commercially available zeolites are known as permutides. So this process involves a reversible exchange of cations. Focus on this term, okay, students. So in this process, only cation can be exchanged between the stationary zeolite bed, in this figure you can see, and the external while liquid. Okay, so after the treatment process, the soft water is collected through this filter and the waste liquid is rejected. In this process, the reactions involved, like whether the water contains calcium salt or magnesium salt, it will be uh, temporary or permanent. It reacts with Na2Z, that is zeolite, and forms CaZ or MgZ and the respective sodium salts. So this process removes both temporary and permanent hardness, as just I have said. The advantage of this process is that after exhaustion of this zeolite bed, okay, the same can be regenerated by simply pressing a 10% solution of sodium chloride, is known as brine, through it. So this CaZ or MaZ, when passes through brine, treated with brine, it becomes NaZ. So these further can be used in the next zeolite process. So the advantages are of zeolite process are it is efficient for removing calcium and magnesium ions, easy regeneration using common salt, surge formation, it is very important advantage, compact and space saving system, suitable for domestic and small scale use, and produces a clear or soft water with very less amount of residual hardness. But disadvantages is of this process is not suitable for acidic or iron or turbidity rich water. It does not a dissolved gas like carbon dioxide or hydrogen sulfide. It requires pre-treatment. Okay, this is the sodium content in treated water that comes due to the formation of NaCl. Regeneration and media replacement cost large scale use is very high, and it may be ineffective if the zeolite wave become foul or clogged. That means like if it becomes foul or clogged. So in this slide, the third process we will discuss, that is the ion exchange process. So this process involves a reversible exchange of ions. Now here the cations as well as anions both can be exchanged between the stationary ion exchange resin columns. Here you can see in this figure, the first is the cation exchanger column and second is the anion exchanger. They are connected serially. Okay, so these resins are actually the insoluble cross-linked long-chain organic polymers. So first the raw water, hydrous containing raw water is inserted, and finally the deionized water is collected. This cation exchanger can be regenerated using acid like HCl, and the anion exchanger after usage it can be regenerated using gases like a wedge. Okay, so based on the active functional group present in the resins, the ion exchange resins are of two types. First is the cation exchange resins, which have the acidic functional groups. So they contain hydrogen, and this hydrogen it can be easily replaced by calcium or magnesium cations. And some other resins contain the hydroxyl group and sometimes the amine group, which are further replaced by the chloride and sulfate. That is the anions that causing hardness. Reactions are like in this cation exchanger, hydrogens are replaced by calcium or magnesium. The anion exchanger, hydroxide is replaced by chloride or sulfate. And after the use this cation exchanger resin or this anion exchanger resin, it can be easily regenerated. Cation exchanger is regenerated using HCl and anion exchanger can be easily regenerated using NaOH. So the advantages of this ion exchange process is very important that it removes all hardness. That means almost zero residual hardness. It is highly efficient with hard water. This is regenerable using NaCl solution. It removes the other metal ions like iron and magnesium. No sludge formation is there. It's a compact system and easily automated. But it also have some disadvantages like initial setup and using cost is high, not suitable for turbid or particulate rich water. The sodium content in the output water is increased. It also does not remove any type of carbon dioxide or H2S gas. It requires regular regeneration. Brine disposal during regeneration may affect the environment further. But still, if we compare these three processes among themselves, okay, that is the lime soda process, permuted process, and ion exchange process, we can see the chemical requirement is there in all three cases. That is lime soda process requires lime, soda, and coagulant. Permuted process requires the zeolite bed, and ion exchange process requires the cation and exchanger resins. So chemicals are required, but the exchange of ions, if we talk about, then in lime soda process there is no exchange of ion. In permuted process, only cation can be exchanged, but in ion exchange process, cations and anions both can be exchanged. So here it is the most efficient process according to exchange of ions. Capital cost in lime soda process is lower. Then from permuted to ion exchange, it becomes higher to very high. But this is very much important point, that is the residual hardness, that is the remaining hardness after treatment. In lime soda process, it is almost 50% residual hardness. When it comes to permuted, it becomes 10 to 15, and in ion exchange process, it is almost 0 to 2 ppm. So by actually discussing, by comparing all these factors, we can say the ion exchange process is maximum effective in water treatment process, then comes permuted, and then lime soda. So this is all about the topic water chemistry that I all have discussed. So I think all of you have understood all the topics I have discussed. If you don't understand any topic, then feel free to ask any question. Okay. So I think there is no question. So let's do this task problem. In a zeolite process, 10,000 liter of hard water is passed through zeolite bed for softening. Now to regenerate the exhausted bed, 200 liter of brine is required. So what is the hardness of this hard water? So you all try to do this problem in your own. I am just giving the answer here, that is 1709.40. Okay. So these are the further topics I will discuss in the next part of this video. Okay. And that's all for today. Thank you. Thank you everyone.